Hello and most welcome to Heidegger 1280. We are strolling on with Roberto, Mangabeira, Unger and Smolin's A Singular Universe. And it's also some very good news. I tried out Smolin and Roberto Unger yesterday with the Swedish quantum physicist Stefan Mangold, also the author Vad väger en tanke, and it turned out very well. I would try to put it on different channels. Among this YouTube channel there will be no video because I wanted to try out the new microphone and I hope it worked out well. I will also add to this the quantum mechanics of the present, a little paper by Smolin and Clara Verde, or Clelia Verde, odd name, Italian. They are also from the Parameter Institute. She's from Milano. I continue where I left off at page 310. This is the first paragraph. The use of statements about connections outside time to represent phenomena in time is not just an aspect among others of the problem of the unreasonable effectiveness of mathematics. It is the kernel of that enigma. The enigma has an explanation. In fact, two explanations. One psychological and evolutionary, the other methodological and metaphysical. Before exploring them, before exploring them, however, I must go further in depicting the war that mathematics wages against time. Mathematics deals with nature as well as with itself. However, it addresses a nature from which time, and together with time, all phenomenal distinction have been sucked out. The world that it represents is neither the real one nor another one. A domain of timeless mathematical objects. It is the real world, the only one that exists, robbed of time. The subject matter of mathematics is a visionary simulacrum of the one real world. Unlike the real thing, the simulacrum is shadowy and timeless. It is preserved against corruption and change only because it is removed from nature, in which time and particularity rule. How can the analysis of such a proxy for the world prove so useful to the representation of causal relations in the real thing? I later suggest an evolutionary conjecture about why the mind as a problem-solving device could come to be equipped with a faculty for relating structured wholes and bundles of relations to one another outside of time. It requires no such account, however, to understand the explanatory advantages of such a disregard for natural time and natural distinctions. We cannot set aside the particularity of phenomena without also depriving them of their temporality. Everything in the natural world is sunk in time. However, it is only by disregarding both time and natural distinction that we can deal with relations and combinations in the most general form. We can then more easily form ideas and inferences about these general connections, free from the spell of the embodied particular and temporal forms in which we encounter them. We can use such inferences and ideas to explain change and movement in time. They provide natural science with what it could never achieve if its imagination of the possibilities of connection were limited to the forms in which we meet them through our senses or our instruments. But what exactly is it that we address when we deal with a simulacrum, the world without time or particularity? This is the fourth attribute of mathematics. The subject matter distinctive to a way of thinking that sucks the world dry of time. A simple but incomplete answer is that we are left with space and with number, or more precisely, with the connection between number and space. A more adequate and comprehensive answer is that we are left with the most general relations among parts of the world. Structured wholes and bundles of relations. In mathematics, we deal with them in their incorporeal and therefore timeless form. It is then only by exercising a self-critical vigilance that we avoid the pseudo-Platonism that has always been rife among mathematicians. The unwarranted supposition that if we are able to conceive and to reason about them in this abstracted form, and if reasoning about them, we experience a constraint that our axioms and rules of inference seem insufficient to explain. They must be objects of a special type, inhabiting a distinct part of reality. We turn a practice into an ontology. In doing so, we fail to consider a possibility for which there is a much better basis, that the reference of our mathematical notions are not a distinct realm of objects. They are the very same objects of the one real world, viewed from the vantage point of a special way of thinking, one that is blind to phenomenal distinctions and the temporal variations of nature. The temptation to use mathematical analysis and logical reasoning as pretexts for an ontology of mathematical objects is nowhere stronger than in number theory. That the prime numbers are distributed in the manner described by the Riemann hypothesis, or that according to Hardy's result, an infinite of zeros of the Riemann zeta function lie on the critical line may seem to be facts of the matter as much as any fact about nature. Indeed, they are as much brute features of the world as that water freezes at 32 rather than at 31 or 33 degrees Fahrenheit. it does not follow, however, that the truths that they announce apply to a special category of entities rather than to the same natural world in which 32 degrees Fahrenheit is the freezing point of water. It turns out that in a world characterized by the postulates of reality, plurality, and connection, that is to say, a world of discrete but connected phenomena. The relations among the numbers by which we count this phenomena have certain definite and surprising relations. We could, by convention, invent a symbolism and a way of connecting these symbols in which other relations would hold. However, this symbolism would not be the powerful and dangerously seductive mathematics that has made the fortunes of physics. It would not refer even by the starkly selective mechanism of this mathematics. It would have rules and constraints as games that we invent do. But it would be no more than a game of our own invention. To understand what is at stake in the distinction between this conception and the ideas that it superficially resembles. It is necessary to grasp the relation between number and space, arithmetic and geometry, the two perennial starting points of mathematics as Leibniz saw. Space and number are intimately related. Our ideas about number are ideas about the one real world in just the same sense as are our ideas about space. Moreover, each of the two sets of ideas is parasitic upon the other. The world as a differentiated structure exists in spatial extension. Its spatial extension is the condition of its variation. There is not just one thing, there is plurality. Although the nature of this plurality may change, it is not just the range of difference that exists, but also the ways in which different parts of the world differ from one another, as well as the ways in which they turn into something different from what they were before. The variable complexity of the world turns out to be decisive for the reality and the nature of time. One way to understand time, I have argued, is to think of it as the transformation of transformation. Time is real only insofar as change is uneven. It cannot be uneven, even if there is just one thing. At least with respect to change. Rather than there being many things, it is space or spatial extension, ground of number, and the substance of its relation to space. We do not count objects in another world. We count them in the only world that there is. In this world, the numerical relations and the spatial dispositions are two sides of the same thing. The correspondence between geometry and algebra is not an accidental invention of early modern mathematics. It reveals an important truth about nature. The numerical relations that we then discover, such as the facts about the distribution of prime numbers, are not facts about a realm of mathematical objects. They are facts about the only world there is, although they are, so to speak, second-ordered facts. They are not facts about the interactions among the natural phenomena that make up nature. They are facts about the second order or higher level relations among the ways of numbering, counting, or quantifying that are suggested to us by such interactions. They are neither facts about a world other than us, than ours, nor made up free constructions. They are facts about this one real world. Although facts about what this world looks like to us at one order of remove. The order of remove established by the special perspective of mathematics. This order of remove does not save them from having the same startling, it just happens to be that way, character of ordinary natural facts. An implication of this view is that there is a basic asymmetry in the relation of mathematics to space and to time. Its relation to space is intimate and internally connected with number. Its relation to time is distance and external, even when movement and change in time are. As in the original applications of the calculus, the very subject that the mathematical reasoning is used to represent. The history of 20th century physics shows the influence of this asymmetry, even when it proposed to connect space and time, and to deny that space-time could be understood as an absolute and invariant background to physical phenomena. Twentieth century physics spatialized time rather than temporalizing space. The use of a
spatial metaphor to describe time as a fourth dimension is a crude manifestation of this bias. Its most significant expression, however, is persistent equivocation about the reality of time. One of the results was and is the reaffirmation, mostly unthinking, but sometimes considered, of the idea of a timeless framework of natural laws underwriting our causal explanations of nature. Mathematics is deficient in the imagination of time and of temporal continuity. As well as of phenomenal particularity. Realities central to nature and therefore to natural science. It has, however, excelled in representing the infinite. The taming of the infinite was one of the greatest achievements of 19th century mathematics. Ever since a view seeing mathematics as the oracle of nature and the prophet of science, and seeing science, including cosmology, as applied mathematics, excuse me, looks for the mathematical infinite in nature. It cannot find there the infinite, not at least the infinite for which it is looking. Take some tea there. This is slowly happening when you're realizing how unimaginably wrong this is in some ways. With a Newtonian paradigm, you just burst out laughing. It is partly real, maybe some inner limits that gets opened up. The absence of any counterpart to the mathematical infinite in nature signals the unyielding limits to any parallel between mathematics and the natural world. Nature is prodigal in what mathematics has trouble representing. Singular events taking place in the unbroken flow of time. Mathematics offers as one of its supreme accomplishments the representations of what nature fails to allow, the infinite. The infinite is a mathematical idea, the mathematical representation of the unlimited or the unbounded, when it is not a theological or metaphysical conception or a physical notion with no clear counterpart in mathematics. As many have argued, including thinkers as different as Aquinas, Hume, and Hilbert, the mathematical notion of the infinite has no presence in nature. The exclusion of the mathematical infinite from natural science gains additional significance in the context of the cosmological view presented in this book. Criticisms of the accommodation of the infinite in natural science traditionally begins with the remark that no one has ever observed in nature an example of the infinite as mathematics understands it. The infinite is invoked by loose and illegitimate analogy to the indefinitely large in number, in space, or in time. This invocation often serves the aim of representing or concealing a limit to the applicability of a physical theory. Such is the case with the inference of an infinite initial singularity from the field equations of general relativity. It is the significance as well of the use of the infinite in quantum mechanics. There it is used to make up for the failure to explain what actually happens, as opposed to what might happen at the Planck scale. This conventional criticism fails to reach the root objection to admitting the infinite into science. Everything that exists in nature, including the universe and all of its phenomena and events, results from other events and phenomena in time. Everything, as Anaximander wrote, turns into everything else under the dominion of time. How then could the infinite come to exist, given what we see and know of the workings of nature? The universe may be indefinitely large, and some of its rudiments indefinitely small. Its history may extend indefinitely back into the past and far into the future. There is nevertheless an infinite difference between indefinite largeness or smallness and infinity, or between indefinite longevity and eternity, which is infinity in time no natural event analogous to any process that we observe in nature could jump the gap between indefinite largeness or longevity and infinity or eternity. The universe can no more become infinitely large or infinitely small by becoming larger or smaller. It can become eternal by growing older. Consequently, the infinite could exist only if it always existed. How true. The world could not have become spatially infinite, just as it could not have become eternal. It would have to be spatially infinite or eternal, or both, always. Nothing within the world would be infinite or eternal. However, the world itself would be eternal and infinite. We fall into confusion when we equivocate about the relation between the idea of the universe, of the succession of universes, or of states of the one real universe. And the concept of being, sein, or reality, where or when the universe stops, we imagine that being or some potential for it must continue to exist. We struggle to conceive nothing, and nothing easily becomes for us a shadow or a signature of being. If, for example, the universe is reduced at certain times in its history to an unstable vacuum field, it remains not nothing. It continues to be something. This something has a history extending further into the past and into the future than we can grasp. Before the 13.8 billion years to which we now date the present universe or its present state, and beyond its conjectured future, heat death, and imagined contraction and rebirth. For science, the universe and nature are one and the same thing. If we allow for the complication introduced by the existence of bubble or domain universes. For science, the whole of the universe, observed and unobserved, and of its history, known and unknown, is the world. Nothing can be outside of them. We may nevertheless think that something is outside of them, at least a potential for being, and even for a particular kind of being. this way of thinking may seduce us into believing that the world must be spatially and temporally infinite, and that the infinite must be conceived in mathematics only because it is also present in nature. Science, however, is powerless to solve the enigma of being. It cannot legitimately dispel the factitiousness of the universe and of its history. There happening to be one way rather than another, by inferring their attributes from supra-empirical constraints, as rationalist metaphysicians such as Spinoza and Leibniz claim to have done. It cannot, by its own devices, pursue either being or becoming. Beyond manifest nature.
Some coffee.
It cannot represent manifest nature to form part of a larger narrative or a more fundamental regime, to which, inspired by mathematics, it then assigns the attributes of infinity and eternity. Neither, however, does science have any basis on which to trump or prohibit other channels of experience and insight by which, outside science, we may try to push our luck against the mystery of being. The self-denying ordinance that is the source of its power provides no license to impose that ordinance on the whole of experience. Scientism is not science. It should have no place in the temporal naturalism espoused in this book. The postulates of being, of plurality, and of connection, which figure in the proto-ontology or the anti-ontology sketched earlier, described minimalist working assumptions of science. These working assumptions say nothing one way or another about the infinity or eternity of the universe. Once we have overcome these confusions, we can acknowledge with greater clarity the objections to claims of eternity and infinity in nature. The problem in supposing the world to be infinite or eternal, or both, is not just that we could never know that the world is infinite or eternal, given the infinite difference between indefinite largeness or longevity and infinity or eternity. The problem is that the overall character of nature would be at odds with nature as we encounter it. Piecemeal, through science as well as through perception. We may unjustifiably feel driven to this extremity by the difficulty of accepting or even conceiving the apparent alternative to it. That the succession of universes or of states of the universe is temporally finite, even if geometry now allows more readily to understand how it may be spatially finite. In parenthesis, the unacceptability of these contrasting and seemingly exhaustive options was the quandary that Kant sought to capture in his first cosmological antinomy, in an epoch in which the spatial finitude was as hard to grasp as its temporal finitude. There is, however, another unassuming alternative which we reject only when we rebel within science against the limits of science and try to turn it into something that it cannot become. According to this alternative, the one real universe is indefinitely large, and the succession of universes or of states of the universe is indefinitely old. Nothing is gained for science, and much is lost by importing the mathematical idea of the infinite and by using it to disguise ignorance as pseudo-science. The preceding argument about the finitude of natural processes deals with only one conception of the infinite. The view of the infinite as unlimited, or the unbounded, that is suggested by mathematics, This view is far from being the only one. On other understandings of the infinite may exist in nature. The natural presence of these other versions of infinity, however, rather than reinforcing the parallels between mathematics and nature, highlights the distance between them. Consider, for example, Aristotle's notion of the infinite as that which cannot be traversed like a treacherous river or a uniform circular race course. The infinite on this view is that which always has some part outside it, as distinguished from that which has no part outside it. It is that which is never completely present, because it exists in time and goes on. In Aristotle's vocabulary, inseparable from recognition of the reality of time, and informed by his imagination as a metaphysician who was also a biologist, the infinite always exists potentially, never actually, and over time, as applied to temporal events. It refers to their incompleteness and open-endedness, and therefore requires an idea of indefinite continuance rather than of eternity. If by the infinite we mean some such feature of nature, then the infinite does indeed exist in nature, at least in nature as it is represented in a view like the one that we develop in this book. The universe may be infinite in this sense, because, like Aristotle's treacherous river, it cannot be crossed. This infinite, however, far from being an import from mathematics, is incapable of full representation, if only because of its temporality in mathematics. It is a physical idea that can be translated only in part into mathematical language. On the view defined by the preceding discussion of its attributes, mathematics is neither invention nor discovery, not at least in the sense in which mathematical invention and discovery have traditionally been understood. The conceptions of mathematics as discovery and as invention each contain elements of truth. Nevertheless, an adequate account of mathematics cannot be developed as a combination of these elements. It requires a different point of view, one that it supports and receives support from. The ideas of the singular existence of the universe and of the inclusive reality of time. Consider first the aspects of truth in the notion of mathematics as innovation. There is no realm of entities outside nature that mathematics could have for a subject matter. Nor can its subject matter be simply our faculties and practices of reasoning and inference. They are too large and indistinct to mark out a specific approach to reality. We can narrow the field further by saying that mathematics is reasoning and inference. with respect to number and space, and more generally to structure wholes and bundles of relations. Even then, however, we have left much too much room to distinguish the mathematical from the non-mathematical. If, on the other hand, we insist that reasoning with respect to number and space be deductive and axiomatic, we have gone too far. There is much in mathematics that is not deductive, and an even greater part that is not axiomatic. By exclusion and in desperation, we may be driven to conclude that mathematics is defined by its history as well as by its focus on only the most general and abstract parts of reality. Taken together, the focus and the history leave a vast margin for maneuver and innovation. The availability of that margin is the truth in the view of mathematics as invention. Consider now the pieces of truth in the notion of mathematics as discovery. Mathematics does have a subject matter. Its subject matter is not simply itself, despite the preponderant role that what I later call internal development has played in the history of mathematics. Its subject matter consists in the most general and abstract features of the world, the ways that the relations among discrete entities are bundled into larger wholes or unbundled into discrete and therefore countable fragments. Mathematics achieves this focus by abstracting in the formulation of its concepts and in the way of connecting them to one another through chains of inference from both phenomenal distinction and time. Such abstraction may make mathematics more rather than less useful to representation of events that are both temporal and phenomenally distinct. The second element of truth, just take some, just give me a second. Sorry. The second element of truth of mathematics as discovery is that branches of mathematics do not develop conjecture by conjecture, theorem by theorem, or inference by inference. They develop discontinuously. Each new field or approach, like a new style in the history of music, comes laden with a certain structure, not just a distinct set of conceptual tools, but also a range of combinations and applications. The content of this structure does not become evident instantaneously. It takes time to be grasped and described. To explicate and develop it either through its application to its own problems and propositions, or through its application to problems in natural science is the work of mathematicians when he is not inaugurating a new area of mathematics. That mathematicians must submit to the discipline of an established branch of mathematics with which he engages may seem no more than a truism. Take the creators of a branch of mathematics find that the creation comes with its own intrinsic properties, potential and constraints, and even its own repertory of inferential moves, is much more surprising but no less true. When this fact is then combined with the distinction between time-bound causal explanations and timeless mathematical connections, it is easy to fool ourselves into thinking that mathematics is prospecting of a realm of being outside tangible and visible nature. Recognition of the rigid and intrinsic properties of each field of mathematics then becomes an invitation to vulgar Platonism. In this respect, mathematics is no different from natural science. Any large theory is distinguished by its research agenda and structural possibilities and limitations, all of which become manifest only over time in the course of inquiry. It is a mistake to attribute this feature of mathematics to the role of axiom-based thinking. Mathematics can never be fully rendered as an axiomatic system, and axiomatic reasoning plays only a modest and marginal role in its endeavors. The subordination of mathematics to axiomatic reasoning would, on the contrary, result in the effacement of the distinctiveness of different mathematical disciplines and in their reduction to standard logic and deductive inference. A third fragment of truth in the view of mathematics as discovery qualifies and complicates the second fragment. The differences among parts of mathematics are real, and the content of mathematics is rich, precisely because mathematics is always more than a formal axiomatic system in the making. It is a way of thinking about reality and of representing it from a unique perspective. The perspective of forgetting about the particularity of phenomena and their placement in the flow of time. It is not deduction, it is the use to which we put all our forms of inference, including deduction, abduction, and induction, when we are disposed to accept the limits and the promise of such a singular austerity of vision. In this sense, mathematics is discovery of the world. When we view the world in a certain way, this way is useful to the development of our causal explanations, precisely because it is not and cannot be causal. It cannot be causal because it abjures time and phenomenal particularity alike. It may seem at first that this account of the elements of truth in the ideas of mathematics as invention and as a discovery moves in the direction of a synthesis or a halfway house between the two ideas. it does so, however, only by relying on a conception that is alien to the traditions of thought from which each of those approaches emerged. This conception so radically alters the meaning of both invention and discovery that there is as much reason to view the outcome as a repudiation of both the ideas as to see it as their marriage. I wonder if I have time to make a concluding remarks. If mathematics exhibited only the first three of the 4 attributes that I earlier enumerated, its pervasive practice of explication, its devotion to recursive reasoning, its fertility in equivalent propositions, we might be justified in taking something from the view of mathematics as discovery and something from the view of mathematics as invention, and in using each to make up for the inadequacy of the other. In this undertaking, however, we would have missed the most decisive and unique feature of mathematics, and the one by virtue of which it can be neither invention nor discovery, as they are conventionally understood. This feature, the 4th feature of mathematics, is the study of a simulacrum of the world, of the only world that there is, a version from which the flesh and flow of things have been wiped away. And this is one of the great advantages of slowly reading this text, because it takes time to change a habit of a lifetime. It needs diligence, enormous dedication, stubbornness. But I see now, and I will get back to that in another lecture, the faults that Julian Barber made in his review of A Singular Universe. he said that mathematics is absolutely apt for descriptions, because when he passes through the border control to, for instance, Italy, the machines will recognize him, and together with his passport identification, the biometrics immediately see him as the particular being he is. That is Julian Barber. What he did in that counter-argument was to reverse. He started with mathematics and then went on to prove that it is capable of the particularities that once created mathematics. It's a circular argument in some open way. It's not an easy circle to understand, but there is circularity there. He turns things upside down. History created mathematics. Particularities created mathematics. And although mathematics does not recognize those particularities, it is still an incredibly useful tool. And I would say that it becomes even more apt and honored for let mathematics be this fantastic tool it is. And Platonism makes a major disservice to mathematics. It stalls its development if mathematics is even an it. There are as different disciplines within mathematics as there are within physics, chemistry, biology, or even more so. And forcing it to have one single purpose, like Gödel somehow tried to do, is strangling mathematics. And this is also the counter-argument for multiverses. Might seem harmful, harmless, but it's draining, and it puts a strain on physics, puts limitations. It is a little bit, Max Tegmark put his foot down and say, we already know everything. That's not a constructive way of starting. And as you all know, it's not unheard of. This is what assumingly Lord Kelvin said in the 1880s. This is what was said to a younger version of the later Nestor in quantum physics, Max Planck, by his own tutor. Don't go into physics. Sie sollen nicht in Physiken einsteigen. I end here and I wish you a very pleasant afternoon. It's already afternoon. And the sun is slowly coming up. And here we have this gentleman doing something. Not quite certain what it could be. My guess is that he's moving a drone.
I say thank you very much.